Hello, this is just a summary on all of exponential functions. I'm gonna erase unit 4 just in case it's not always called that. So this is everything from the exponential functions unit. So we're starting with simplifying expressions, and we're gonna use some exponent laws that we learned, and there might be some rational exponents in there, so we'll deal with those. Okay, we got multiple approaches here, but I'll just go with what I would do. So here we have a giant thing going on. I think I'm going to simplify inside the brackets first, just to make it look a little better. So 3 over 6, I could simplify to a half. So I'm going to put the 2 down there. I'm not going to put the 1 because there's going to be other stuff up there. Then x to the power 4 divided by x, I could subtract those exponents, which would leave x cubed on top. And then x to the power of 8 divided by, y to the power of 8 divided by y to the power of 11 would leave me with y to the power of negative 3. Or I could keep that in the denominator as y to the power of positive 3. Okay, and then the whole thing is to the power of negative 2. So I think I am going to do my little trick of flipping this whole thing. And then I can make my exponent positive. So now I've got 2y cubed divided by y to the power of 3, all to the power of 2. Okay. Next, I'm going to square everything. I'm going to put everything to the power of 2. So that will leave me with 2 squared, which is 4, y to the power of 6, and x to the power of 6 as well, or yeah, to the power of 6 as well. And that's all I can do. That question's done. Okay, so let's look at the next one. This one is the power of 3/4, a rational exponent. Okay, so I'm going to tackle the numerator first. I'm going to apply the exponent to everything inside the brackets, all 3 of those guys. So 16 to the power of 3/4 is really like the 4th root of 16 to the power of 3. And then if I multiply these exponents, negative 8 times 3/4 times 3/4, I would end up with negative 24 over 4, which would just be negative 6. So this will become x to the power of negative 6. And then the next one I have to multiply is 3 times 3/4, which will end up as 9 over 4. And then my denominator is still the same, xy squared. Okay, it looks kind of messy, so let's clean it up a bit. So I know the 4th root of 16 is going to be 2. So that's going to be 2, and then it's to the power of 3. So 2 to the power of 3 is 8. And then I'll take care of my x's. So I've got negative 6 and 1 on the bottom. So negative 6 subtract 1 is negative 7. So I'm going to take that whole x situation and pop that guy in the denominator. And I'm going to make it x to the power of 7. Okay, then I've got y to the power of 9 over 4. And y squared. So I need to subtract those exponents. So let me just show you that over here. So I've got 9 over 4 and I have to subtract 2 over 1. So I'm going to make my denominators the same by multiplying my second fraction by 4, which will make it 8 over 4. And that will just equal 9 minus 8 is 1. So I'll just end up with y to the power of 1/4, or the 4th root of y. And that's probably how I would leave it. I don't think it's wrong if you were to write it like the 4th root of y, like in that format too. I don't think it matters. And that's it. Moving on. We also have to know how to graph exponential functions with different bases. So in this case, it might be just handy to make a table of values. So we summarized that if b, the base, is a big number, like 2, 3, 4, 5, 6, 7, 8, 9, 10, we've got an increasing function, which means it's going to be going up to the right, like that. So we're going to call that increasing. So I'm just going to throw in some x values and see what they would be when I sub them in. So 4 to the power of -1 would be the same thing as 1 over 4, or 0.25. 4 to the power of 0 would just be 1. 4 to the power of 1, 4. 4 to the power of 2, 16. So I can get an idea of what this graph's going to look like. So at -1, I got a quarter. At 0, y equals 1. 1, 1, 2, 3, 4. I'm not going to fit the next one on my graph, so I'll just sketch it now. It's going to look like this. Sorry, I'm having some stylus problems. So I can see I've got an asymptote, some key features. I've got an asymptote at y equals 0. That's where my asymptote is. Got an increasing function with a domain of x can be anything. X is a real number. And my range is y has to be greater than 0, and it's also a real number. So let's just check out what happens if we have a decreasing function. So right away we can see that the base is a number between 0 and 1. So we're going to have a decreasing function. It's going down towards the right. So I'm going to put some more negative values because I know it's going to be bigger in the negative side. All right, so if I've got -2 for x, I know that's going to equal 4. -1, a half to the power of -1 is the same thing as 2 to the power of 1, so 2. Anything to the power of 0 is 1. A half to the power of 1 is just a half. And a half to the power of 2 is just a quarter. Okay, so I'll just I'll just quickly graph that. 1, 2, 3, 4, plot those points. Half, a quarter. So it's gonna look like this. Sorry, my graphs are rough. So I still have an asymptote down here at 0. And my domain is the same as the red graph, and my range is the same. So that's how we graph exponential functions with different bases. Transformations. Okay, what if we have, this is our parent function, half to the power of x. So we know that looks like, I think we just graphed that. So we know it looks, oops, sorry. We know it looks like this. It's a decreasing function. It's gonna look like this. That's what our parent function is gonna look like. Now, if we want to graph our transformed function, let's point out what's happening. So this negative in front of the half is telling us that we're going to have a reflection over the x-axis. So now this entire graph is actually going to look more like this. That's what a reflection over the x-axis does. Just flips it right over the x-axis. So I know that the point that was once here is now going to go down here. So our graph's going to look like that. That's one thing that's going to happen. Another thing that's going to happen is this -3. So that's going to shift our graph down 3, which affects our asymptote. So we're going to have an asymptote now at y equals 3. -3, sorry. So let's pop our asymptote on there, right at -3. It's nice to draw that on. And it's always going to be where the c value is in our transformation, right there. And then the only other thing that's happening is a reflection in the x-axis. So my point that was once here at 1 is going to just get shifted down 3. So it's just going to be here now. And then I'm going to have the same... It's this, there's no stretches or anything. So like I don't even need to sub in values for x or anything. Like I can see it's going to follow the same kind of pattern, but a reflected one. So I know I'm going to have a point here. And I'm also going to have a point here. And then it's just going to get smaller on this side. So I know exactly what my graph's going to look like. We always want to make sure we plot the y-intercept correctly. And my y-intercept would be at 4. If you're not sure how to find the y-intercept, that's crazy. You always just sub in x equals 0 for any function. It doesn't matter. That's the definition of the y-intercept. What is the y value when x is 0? So you can literally just sub that into your equation if you need to. Determining equations. Let's determine two different equations that could represent this function. Okay, so I'm going to look at this function. So I see I've got a y-intercept at 1. I've got an asymptote at y equals 0. And then when x is 1, y is 2. When x is 2, y is 4. So I know just from like graphing a bunch of these and knowing exponents that this graph could just be as simple as y equals 2 to the power of x. That could totally be this graph. But what if I wanted to make another equation that was still this, it was this graph also? Okay, well, I'm going to use my knowledge of decreasing functions and reflections over the y-axis to say this function, y equals 1/2 to the power of negative x, could also be this graph. Because remember how 1/2 to the power of x would look like this? So if I put a reflection in the y-axis, it's just going to flip it so it looks like that. So those are going to be actually identical. And it kind of makes sense too, right? Because if you have a negative exponent, just like thinking about exponent laws, I can make that exponent positive by flipping over my base and raising it to a positive exponent. So even using exponent laws, we could prove that those equations would be the same. Okay, let's determine an equation that would have an asymptote of 5 and no x-intercepts. Okay, just any random equation. Cool. Let's graph it. 1, 2, 3, 4, 5. Should have put my graph a bit lower, I guess. Okay, let me just move it down. Okay, so I've got an asymptote here, right, at y equals 5. And I don't want it to have any x-intercepts. So therefore, like, I don't want my graph to go this way because it's going to have an x-intercept. So I'll need my graph to go, it can either look something like this, or it could be a decreasing function. It doesn't really matter, as long as it's on the top, above the asymptote. So I'm just gonna do an easy one. Why not? So I'm gonna make it a graph of like y equals 2x. Like that would be my parent function. Y equals 2 to the power of x. And then I'm just gonna add an asymptote of plus 5. So I've just raised it up 5. There you go. But there's like a bunch of different graphs you could have. You could really have any left-right transformation. You could have a y reflection. There's so many options. You could have a vertical stretch. Just like an infinite number of equations you could come up with. This is just one idea, a simple one. Okay, solving exponential equations. So our goal here is to make the bases identical. This is really irritating. I can't lean my hand on the iPad. Okay, so I have a base of 3 over on the left side and 9 on the right side, but I want them to be identical. So in my mind, I'm thinking, I'm going to look at the bigger number, 9. How could I write 9 with a base of 3? I know. 3 squared is equal to 9. So I'm going to replace this guy with 3 squared. So I'll get 3 to the power of 2x minus 4 equals 3 to the power of 2. That's my new 9. And it had an exponent of 3, so I got to keep that. And I'm just going to simplify it using power of a power law. I'm going to make it 3 to the power of 6, because 2 times 3 is 6. Okay, so now, as soon as my bases are the same, I can just make my exponents equal to each other. So 2x minus 4 equals 6. Now I just need to isolate x, and I know the answer. So I'm going to add 4 to both sides. So I got 2x equals 10. And then I'm going to divide both sides by 2. So now I know x is equal to 5. And I could go back to my original and just double check. If I want, like sub it in. So 2 times 5 is 10 minus 4. So 3 does, and I could check, does 3 to the power of 6 equal 9 to the power of 3? So you could like actually calculate it and see if it's true. And that's how we solve exponential equations. Growth and decay. This is the last thing on the test. So I broke it down into this strategy here. So we got our main equation, like this guy in the box. This is what they're all going to look like for now. y equals a times b to the power of x. A is going to represent our initial amount, whatever amount we start with. And b is going to be our base, which is going to be like deciding what our function is increasing or decreasing by. Y and x are going to stand for whatever, depends on the context of the question. It could be like population and time, number of bacteria and time, like something like that. Okay, so I split it into kind of like 3 sections, I think. So it seems to me that questions are either percent stuff. So the question might be saying, hey, your bank account is like your interest rate or something. I don't know. Is you get like 3% per year or something. So you could have some kind of percent question. In which case, you would need to get your base by doing this. Convert your percent to a decimal, 0.03. And then add a 1 to it since it's growing. 1 plus 0.03. So in this case, your base would be 1.03 for B here. And you'd still have an initial amount and stuff you're trying to find out. But let's say you're having a decay of 3% over time. So it's going to be similar. You're going to represent it as a decimal, but the base is going to be 1 minus 0.03, which is 0.97, which is saying like you have 97% of your original amount every year or every however often. So that's how you do growth and decay if it's percentages. That's how you could find your base. Then there's like specific questions on bacteria, it seems like, and radioactive isotopes. So often bacteria doubles as it grows. So if something is doubling, your base is going to be a 2. If something is tripling, your base would be a 3. And then often it's got this other thing to it where there's something called doubling time. So if it says like you have bacteria that's doubling every 4 hours, you're not just going to have a straight x as your exponent. You're going to have like, okay, this bacteria is doubling every 4 hours. So you're going to have a t over 4. If you want to find out how much is left after 12 hours, then you can input a 12 for time, which means it will have doubled 3 times. So that's why we have the fraction exponent there. Half-life is similar. So you only have half of whatever you started with every time period. So the base is a half. We put a denominator of h because sometimes it doesn't just decay by a half every year, let's say. Maybe it decays, or maybe its half-life is like 3 hours. So every 3 hours it's getting cut in half. So similar to this bacteria thing, we have a fraction as our exponent. So I would say if you can understand like everything in this section here, you can probably solve most exponential growth and decay problems. So let's try one. Ray spent $250,000 on a car. That's crazy. The car's worth falls exponentially at a pace of 5% every year. I just made this up, so I think it's very accurate. How much is the car worth after 3 years? All right, so we've got an initial value for this car. You don't have to use y and x too. You can say like, I don't know, amount of money the car is worth equals. Well, initially he spent $250,000. So that's the initial amount. How much is it going down by? It's decreasing 5% every year. So to find our base, we would do 1 minus 0.05. So our base would be 0.95%, or 0.95, sorry. So our base is 0.95. And we want to know how much the car is worth after 3 years. So we're just going to raise it to the exponent 3. And then we're just going to calculate that. Or should I calculator? Okay, so 0.95 to the power of 3 times 250,000 equals $214,343.75. So after 3 years, that's how much your car is going to be worth. I think it just probably decays a lot faster than that. So yeah, that's how you do exponential growth and decay questions. And just beware, because sometimes you might not be looking for the total amount. Sometimes you might be looking for the time period, which is annoying, because then you have to kind of guess stuff. Or maybe you're looking for the initial amount. Who knows?